Welcome, pre-calcers. We are going to do some some in-depth math with algebraic modeling here, and we're going to be kind of merging that with some geometry. So kind of some cool stuff today. Something to note is that you are going to need a calculator for this, so please have it near and dear to you, and we'll get started. So for number one, we're asked to consider one leg of a right triangle is twice as long as the other. So let me start with the picture here. Whenever you're given a lot of words, condensing it down into one image is going to help you be able to think about a problem a little bit faster. So we're asked to write an equation for the length of the hypotenuse, the longest side, and we'll call that h, as a function of the length of the shorter leg a. So according to my diagram, this looks like it's the shorter leg. The other leg is twice as long. And then we're trying to find that or define that in terms of the hypotenuse. So you have to think about which equations pertain to right triangles, most notably Pythagorean theorem. So that we have the shorter leg plus the other leg, make sure that quantity is squared, is equal to the hypotenuse squared. From here, we're going to define h explicitly by solving for it. I'm going to simplify my exponents, so I get a squared. I'm going to rearrange it so h is alone. Take a square root, a squared plus 4a squared. Note that when you take a square root, there is a positive and negative case, but in this case, when we're talking about a geometric formula here, that is only going to pertain to the positive case because distance is always positive. Lastly, we can combine like terms and write this in function notation. And we get the square root of 5a squared. You might notice here that there's an a squared under the square root, which you can simplify since this is a product. So if you would like, you can also write your function like this. And we have answered our question. Let's rock and roll on to question 2, another geometry one. Lucky us. A square is inscribed within a circle. If you are doing these notes on Notability, you are lucky because if you draw a circle and hold it, you get a beautiful one. And then we're asked to inscribe a square so that each vertex touches the circumference of that circle. And then we're asked to write the area of the square as a function of the radius r of the circle. Something to consider here is that the area of a rectangle is going to be the length times the width, which in this case is not the radius, but let's put the radius in there. Here's the center. The definition of a radius is the distance from the center to the perimeter. So we get this segment. This is also a radius if we look around this way. And if we kind of divide up the shape into 4 congruent parts, we can do that with our radius. Strictly by the definition of a radius, we know that these are all congruent. If you remember your properties from your freshman year honors geometry, you know that these are perpendicular bisectors, and they intersect at a 90-degree angle. Meaning this is an isosceles right triangle. Each of these angles are 45 degrees because if the legs are the same, the base angles are the same. And if I'm thinking about this in terms of my radius r, I know that the hypotenuse is going to be r root 2. 45, 45, 90 triangles. These are going to come back big time in Unit 4 at the end of the year. So now, lucky us, we've kind of puzzled our way to find the length of this square. The width of the square is the exact same. That's why you can also write the formula for a square as s squared. That's why it's named that. So if I write the area, doesn't specify what variable to use, but I'm going to use a, and I'm defining it in terms of r. That is going to be r root 2 times r root 2. R times r makes r squared. Root 2 times root 2 makes root 4, which can be simplified to 2. This is my formula for the area of this square. Number 3, consider all rectangles with an area of 220 square feet. Note that we can have some rectangles that are very skinny and some rectangles that are a little bit more even. We're considering the set of all of those possible values, so we're going to represent our rectangle with variables. Here we're asked to consider the perimeter P as a function of the length of one side of the rectangle x. Let's call the length x here. I'll put it on either side since I know I'm going to have to consider the perimeter. Then we're asked to find the dimensions of this rectangle that has the least perimeter. And then we're asked to evaluate what that is. So, thinking about this problem, working backwards, I want to find the perimeter. And in order to do that, I need not only the lengths, but the widths. But they don't really tell me anything about the widths. But something you have to consider for these non-straightforward problems is like, what piece of information haven't I used? What info do you have? In this case, it's the area. We know that the area is equal to length times width for a rectangle. And they give us that the area itself is 220 square feet. We define the length as x, and we can actually use this to define our width in terms of the length. By solving for it by dividing by x, we see that our width is 220 over x. And I'm also just going to put that into our diagram. Now we have enough information to start considering our perimeter. If we do that, we'll see that our perimeter is equal to 2 times the length, 2x, plus 2 times the width. Simplifying this here, this is 2 over 1 times that quantity. So that simplifies to 2x plus 440 over x. Naturally, when we're asked to find the least amount of perimeter, we're asking for when this is minimized. In other words, we're looking for a local min. So at this time, I'm going to do this in Desmos, but please take a second to open up your graphing calculator into your y equals, and we're going to take a look at this function. So say our y value, our output, is equal to 2x plus 440 over x. We get this rational function. We consider when this rational function is at its minimum, and we get this. Our min is at 14.832 about, comma, 59.330. I rounded to 3 decimals here, but make sure to pay attention if it asks you where to round. Didn't tell us here, so I'm just going to go 3 decimal points. Let's actually interpret what this means now, because you might think this might be the length and the width, which case I would say you're half right. Your x-coordinate does represent your length. What does your output represent? That represents your perimeter. So we are asked to find the dimensions of the rectangle and the least amount of perimeter. So we know this is half of our answer. And then to find the width, we're going to use that equation we found with the area to find it. So the width is equal to 220 divided by the length, which in this case is 14.832. 220 divided by 14.832, and I also get about 14.832. Interesting. .833, and we're going to put a units of feet on here. I'm going to put units for feet and feet for perimeter as well. Just pay attention to the units there, and you'll get full points on a skill check. Okay? Lastly, we are going to consider one more example here, which is quite fun. This is kind of like an iconic pre-calculus question that you might see, and it's, I don't know, pretty interesting. I've actually come up with this problem when I've done some baking. When I was baking carrots, I wanted to make kind of a three-dimensional volume. I'll show you what I mean. So suppose we have a square of side length x that is cut out of each corner. So here's each corner, and we're cutting out a square that is length x by x of an 8-inch by 15-inch piece of cardboard, and the sides are folded up to form an open-topped box. Rounded all non-exact values to 3 decimal places. So first is to draw a diagram of the situation. I've already kind of drawn a situation 2-dimensionally of the object right here, but I want you to take a second to think, like, what would this look like in 3 dimensions when you did fold this up? Take a second to pause this video and draw the diagram yourself. Are you ready for the reveal? 3, 2, 1. Looks something like this. I want you to pay special attention to my colors here. These cutout pieces then become the sides that are glued together in pink. This side in green, that is going to be your length, will turn out to be the length of that 3-dimensional object. And same thing with this red side right here. Notice how it does not include the cutouts. Now that we understand this problem and what it kind of looks like folded up, we're going to write a volume function in terms of the cutout x. So if we do that, v of x, the volume in terms of the cutout, is equal to length times width times height. And if we substitute those values in, the length is not 15 inches. It's 15 inches take away 2x. Same logic for the width. You're going to have the length of 8 take away 2x. The height, as you can see when they are glued together, is actually just x. So for thinking about the domain of v, first of all, think about like the zeros. This is not a rational function, so I don't need to think about numerator and denominator, but I'm now going to have solutions at 7.5, x equals 4, and x equals 2. You might say that since this is a cubic, the domain might be from negative infinity to positive infinity, but remind yourself of the context of where this is coming from. Can you have a negative x value? Can you cut out a negative length? No, that does not make sense. Can you cut out a 0 length? What would that look like? That is possible. Because when your x is 0, that's just a 2-dimensional sheet of cardboard, 15 inches by 8 inches. Think about another one of the zeros here. The next 0 that would occur, I wrote x equals 2 when I meant x equals 0. Whoops, is 4. What happens when x equals 4? Well, this would extend to 4 and this would extend to 4, meaning that this would not have a width. It would just be a 1-dimensional length of cardboard. So that would be our maximum value. Anything past that for x values would give us a negative volume, which doesn't quite make sense. I wish it did. Think about that for a second. Now we're asked to graph v over its domain. going to put down my intercepts, 0, 4, 7.5. Think about the end behavior here. What do you think it would look like? We are going to visualize this in a graph because that is going to help us answer these later questions, but it's kind of fun to visualize it yourself. Thinking about the lead coefficient, that's going to be negative 2x times negative 2x, which is positive 4x squared times another x is going to be a positive lead coefficient. So I know my end behavior is opposite. One's going to end down and one's going to end up, and we can kind of use our calculator now to see precisely where that happens. Y equals the quantity of 15 minus 2x, close the parentheses, 8 minus 2x, close the parentheses, times x. I'm going to adjust my window a little bit here. So it kind of fits perfectly. Very nice. And I see that my window for the domain does make sense. And it goes up from infinity. I'm going to draw that with a dotted line just to show the relationship. It comes up to a maximum value and dips back down below 0, only for it to continue back up on the other side of the graph. Beautiful. So D asked us to graph its over domain. Yippee. We did it. And then we're asked to evaluate several functions. So we're asked to find v of 1. I'm going to change this to a function. Let's see if I can actually just type out f parentheses x, close the parentheses, and then I'm just going to evaluate that. So f of 1 is equal to f, no, caps lock. There we go. Okay. F of 1 is equal to 78. F of 3 and f of a half. 3 is equal to 54. And f of a half is equal to 49. Nice integers. Reminder of what those are. That is the volume. So that is going to be, was it inches? Yes, inches cubed. Because it has 3 dimensions. Let's talk about f. F asks us to think about something. Let's find out what that something is. It's asking us where the y values are exactly equal to 80 inches cubed. So the way you do that is instead of considering the x values, you're going to consider the y values. So in your y equals, put in y equals 80. And you're going to consider when that is. I'm going to write these solutions to this system as an ordered pair. So that is 2.346, 80, as well as 1.052, 80. Letter G. For what value of x is this inequality or the volume greater than 65 inches? Again, that's a y-coordinate. 65 is here. And so that's going to be from the interval from the left x value to the right x value. Ooh, I should say that these are ordered pairs, because right now I'm going to write g as an interval from 0.7 2.36. 2x is 2.757. I'm going to pay attention to the inequality sign. This is non-inclusive. It's just a greater than, so I'm not going to include brackets here. And note that this is an interval. Lastly, let's talk about these two ones. Find the maximum volume of such a box. That is this, you wouldn't call it a vertex, but you would call this local max. So it has a local maximum of 90.741 inches cubed. And I had asked us for how big the square should be in order to produce the box of the maximum value. That's what the x value stands for, right? If you look at our original equation, this value for x was the cutout. Again, notice my colors in pink, that it matches there. So my cutouts are going to be 1.6 repeating. So I'm just going to write that as a fraction, 1 2/3 inch by 1 2/3 inch. And that brings us to the end of our notes for today. I miss you guys. I hope you have a good class and a great weekend. Note that you are going to start worksheet 1 right now. You may quietly discuss with your group as you're working through these. Afterwards, you will do a quick exit ticket, which is kind of like a warm-up. Not graded for points or anything, but I'm just using it to assess what you learned from this lesson while I'm gone. Thank you for investing in your education, and I hope you have a great day. Thank you for listening. Bye.